So the full title of this talk is Friendship Ended with Clean Code. Now a philosophy of software design is my best friend. I remember studying clean code when I was a junior developer, and what really stood out to me were the illustrations and the quotations at the start of the book. So they looked a bit like this, and if we zoom in on them, you can see one of the quotations reads, "You can call it beautiful code when the code also makes it look like the language was made for the problem." And I remember finding these quotations very, very inspiring. Of course, it's not enough for a text that purports to teach us how to write clean code to just be inspiring. We needed to actually give us sensible advice for writing legible and elegant code. And I think in the Android community, we do a really good job of recognizing clean code when we see it. So we esteem the elegance and simplicity of the Kotlin standard lib, and we like these open source libraries written by Airbnb and Square and other engineering organizations. And we also love Jetpack Compose. So wouldn't it be wonderful if there was some kind of book that we could use? We could read it ourselves, we could give it to our colleagues, and we could hand it over to the next generation of Android developers. And wouldn't it be wonderful if this book could actually take them to the same heights of quality as these examples that we admire? We're going to talk today about why clean code is not such a book and why there might be other books we can use to help us in our journey. What are we asking for when we want a book to teach us how to write clean code? Really, we're asking for a book to teach us problem decomposition. So if you imagine a problem like the operation of a bidding screen in an e-commerce app, we want to break that big chunk of complexity down into higher level components like classes, and then we want to break down those same classes into lower level components like private functions of that class. So therefore, this talk is going to have two parts. One part where we talk about functional decomposition, and one part where we talk about higher level decomposition into classes. So here goes first part where we talk about functions. So Clean Code has a whole chapter on how to write functions. And this part of the talk is going to follow a blog post I really like called "It's Probably Time to Stop Recommending Clean Code." We're going to start by being charitable to clean code and pointing out the good advice we get from it. So first of all, function names should be descriptive and consistent. That seems like sensible advice. If the functions have obscure names, then it's not going to help us. Output arguments should be avoided in place of return values. That's pretty sensible advice and pretty standard procedure in most modern languages. Functions should be commands or queries, but not both. I think that's also excellent advice. Let's move on to some of the more questionable assertions. So the first one of these is that duplication may be the root of all evil in software. Now, if you've been around a while, you'll probably realize that there's some nuance to be explored here. So the typical way that's explained is that programmer A will see some duplication and they'll think, don't repeat yourself, and they'll just hammer on that duplication immediately and create some kind of abstraction. And after some time, programmer B comes along and has to solve a similar problem, but the abstraction created by programmer A doesn't quite fit, and they just have to hack their work into the abstraction to somehow get it to work. And then this cycle repeats itself again and again, and you just end up with a big mess. So the point here is that programmer A shouldn't have immediately hammered on the duplication in the first step, and they should have waited a while and just explored the use cases. And that's reflected in advice like avoid hasty abstractions, which is sometimes abbreviated as AHA, or sometimes a rule of three. And I think Sandy Metz explains this really well in her blog post and her Rails talk, where she explains that duplication is better than the wrong abstraction. So this is really concerning that clean code right away is giving some unnuanced advice about don't repeat yourself. And this is a book that's supposed to teach us how to write elegant code. Then we get into some really strange advice in clean code. First one is that the ideal function has 0 arguments. So that's immediately giving us advice that contradicts our common sense about what is clean code and what is a nice clean API. So I think most Android developers really appreciate the Compose UI APIs, like the button example we have on the screen right now. And although there's a lot of parameters for that function, I don't think it's a big problem. The parameters all have sensible defaults. It's not really adding a lot of complexity, and it's not dirty in of itself just from having a large number of parameters. So it becomes increasingly bizarre when we're told that the functions, in addition to having 0 arguments, should have no side effects. So if you think about a function with no parameters and no side effects, what's it going to do? It doesn't receive anything from other functions because there's no way to pass information down without the parameters. And then because presumably the other functions in the class are ideal functions as well, it can't pass anything on to them. And you might think, okay, well, what the author means here is that it's talking about side effects in another class, not talking about side effects in the same class. It actually explicitly says that it's talking about side effects in the same class. So very strange advice here about what to do with side effects. Then we have some advice about function length. So the first rule of functions is they should be small. Every function in Kent Beck's program was just 2, 3, or 4 lines long, and that's how short your functions should be. Now, you might think this is just hyperbole, and in general, short functions are desirable, but let's have a look at some actual code examples from clean code. So we're going to have some before code and after code. So this is where clean code has shown us some a bad example, a bad functional decomposition, and then clean code is showing us the proposed refactor, which is supposed to improve the code. So here's an example. It's some code to write an HTML test report, and basically we're saying, okay, there's some setup for the entire test suite, which runs before any of the tests in the test suite, and there's some logic about whether to include that or not. And then there's some logic for including the individual setup before each test case. And then you have the teardown for the individual tests and some logic about whether to include that or not. So if we look at this before code, we can all agree that it's not ideal code. There's some improvements to be made. But let's look at the proposed refactor here from clean code. So there's a few things that stand out. First of those is that it's taking this Boolean parameter is sweet and then immediately performing a side effect on the class by capturing that parameter as a member. And the only reason for that seems to be to make this function down here include to avoid passing as a parameter. So it's trying to make that later function we can see there above line 22, it's trying to make that have 0 arguments. So in order to do that, it's making a side effect on one of the members of the class instead of passing down through other parameters. So we're not going to spend much time trying to refute that or trying to persuade you that's a bad idea, because I think people will naturally tend to write immutable classes or to minimize the mutability of their classes, because the Kotlin language is going to steer you in that direction. But let's look at some other parts of this functional decomposition here. So we can see that the problem has been stated very clearly in almost kind of English language sentences, and each of these four functions here is very, very small, just 1 or 2 lines each. So when clean code says each function should be just 1, 2, 3, or 4 lines long, it really, really means that. And if we could summarize the strategy for functional decomposition in clean code, it's might be something like this. We use these zero argument or zero parameter functions and side effects on members to summarize a problem in a way that approaches natural language, so approaches English. Let's bring another perspective on this problem here. So we're going to look at a text called A Philosophy of Software Design. So the author is John Ousterhout, who is a very acclaimed professor at Stanford. And the book also incorporates advice from a range of luminaries in software engineering. So right at the start of the book, there's a list of people whose advice has been incorporated, and the names that I recognize that stand out were Jeff Dean and Sanjay Gavamat from Google. And the interesting thing about this book is it's empirical or it incorporates feedback. So it's the result of a class taught at Stanford, CS 190, and that class is taught in a very similar way to how we would teach English students or students in English literature to write essays. So when we're teaching students to write an essay at university, we'd ask them to submit a draft, and that draft would be marked by a professor, and then they would get feedback and then resubmit and learn in that way. So this class proceeds in a similar manner. So I think that's really, really interesting, and it's going to give us some practical insights into what makes for a good decomposition. So what's the core tenet of a philosophy of software design? The most important point it makes is that modules should be deep. Now, what do we mean by a module? We're not talking about Gradle modules. We're talking about just a part of a software system. So what do I mean by modules should be deep? Let's visualize two different modules here. The one on the left is like a skyscraper, and the one on the right is like a squat factory. So we're going to imagine the roof of the building, the width of the roof of the building is representing the interface. So that's everything you need to understand in order to use that software component. So if it's a function, you need to be able to understand the parameters and the return type. If it's a class, you're going to need to understand the public contract of that class. So obviously the interface is a cost, and it's something you want to minimize. We want our modules to be easy to use to help us in the battle against complexity. And we're going to imagine that the height of the buildings represents the functionality that the modules provide. So obviously that this is a benefit that you want to maximize. So you can see the squat factory is very shallow, and the skyscraper is deep. We want modules that are easy to use and provide a lot of functionality. So what would be an example of a deep module? Well, one of the best examples that's brought up in the book is the garbage collector in Java. So this has an interface that's effectively invisible to application programmer. It has almost no interface at all. You don't have to turn it on or you don't normally have to configure it in any way. It just magically works in the background. And the functionality is extremely deep. It's going to reclaim the unused memory. And that functionality has the magical property where it simplifies the interfaces in your own application, because your interfaces and your modules no longer have to worry about memory management. So it's a great example of a deep module. In Android land, and I think a really good example of a deep module would be retrofit. So with retrofit, you take one of the functions in your own module and just decorate it with metadata using annotations. Then you call retrofit create, and that magically turns your function into a function able to make the actual HTTP call, to perform JSON parsing if you want that, and to adapt to whatever concurrency framework you're using, whether you're using RxJava, whether you're using Flow or Kotlin coroutines, it'll work with that. So that's incredibly powerful, and it's just a few lines of code, and it's very easy to use. Now, if that's a deep module, what would a shallow module look like? You can see here an example of a shallow method from a philosophy of software design. So this function here, all it does is manipulate a member called data, which presumably is some kind of map. And all it does is assign the string parameter to null. So what's the problem with functions like this? Well, there's no abstraction. That function isn't actually hiding anything from me. Everything that function does is actually visible through the interface, or visible just through the name of the function. And it's no simpler to think about the interface, the function, than to think about the full implementation. So it's no simpler to think about calling add null value for attribute than directly manipulating the data property you see there. Even in terms of keystrokes, it's more difficult to call this function than to call the implementation. And this kind of function is adding complexity in terms of a new interface for developers to use, but not really providing any kind of compensatory benefit by providing some kind of deep functionality. So we turn back to clean code and look at the functional decomposition it proposes. You can see that these functions here, like include setup pages, are not very deep at all. They're just 1 or 2 lines long. And even if we discard things like how that class uses side effects on members rather than passing down, and we just use the inline function refactor in the IDE, we can end up with something that might be a bit more meaningful. So instead of a whole lot of little functions, 4 different functions all extracted out, we end up with one larger function that's maybe a bit more meaningful. So instead of reading all these little functions and trying to mesh together into our heads what they all accomplish together, we end up with a larger function that might be more difficult to read initially, but reading it is actually meaningful. And when we do that refactor, we actually do end up with some code that a deeper function, which is include. So I wonder if that's a better way to look at decomposing that problem there. Now, in Android land, you often end up with a functional decomposition that looks like this. So here's a fragment. This fragment is going to collect some flows on view created. So collect flows looks like this. Collect flows is going to call through to collect view states, and then call through to collect events. And then collect view states looks like this, just a few lines. And same thing for collect events. Maybe it's not the end of the world if we just inline all of that. So another way to look at this problem is abstraction means to draw away. A nice definition of an abstraction would be a simplified view of an entity which omits unimportant details. That implies that abstraction can go wrong in 2 different ways. First is by including details that are not really important. And the second way is by omitting details that really actually are important. Now, if we look at this collect flows function in isolation, you might wonder, like, which flows, when are they collected? You could argue that those are actually important details, and the fact that they're important is suggested by the fact that if I saw that function in isolation, I'd immediately want to go to the definition of the and see the implementation. So just in case you're thinking this is all crazy talk and coming from some Stanford professor, John Carmack actually recommends this strategy as well. So John Carmack is the programmer for Doom from id Software, and he has an article. He says that, okay, if a function is only called from a single place, then you can consider inlining it. Besides, so not only does that simplify the interface, but it means that you can't call that function from a place where it's not intended. So if you think it back to that fragment, it'd be a bit of a disaster if we called collect flows from some other part of the fragment as well. So inlining it actually prevents that problem. So that's our section on decomposition into functions. Now we're going to talk about decomposition into classes, or this larger kind of decomposition. So often when we're talking about decomposition into classes, we are referred to the SOLID acronym for the solid principles for object-oriented programming. And we're not going to explain all of them in detail, but the one that comes up a lot is the single responsibility principle. And the original statement of this is there should never be more than one reason for a class to change. In other words, every class should have just one responsibility. Now, to that, Dan North says, okay, that's pointlessly vague. Any non-trivial piece of code can have a number of reasons to change, which may or may not have include the one that you had in mind. So the point is that you can always find reasons to divide your classes up smaller. So remember how we talked about retrofit having a nice API and being a deep module? Well, here's the cool interface from retrofit. And does this follow single responsibility? Does this have no reasons to change? We can always speculate about reasons to change. So you could argue facetiously that, okay, well, cancellation is a separate responsibility from execution, so you should extract a separate class for that. Not saying you should do that. I don't think you should do that at all. But the point is, you can always find reasons to split up classes, and that is very well articulated in this article from Joe Lynch from Google called The Misunderstood Single Responsibility Principle. And in that blog post, Joe argues often people who like tiny classes will use a single responsibility principle to justify making even tinier classes. And that can actually end up creating a whole lot of complexity because you end up, instead of one single abstraction, you end up with a whole lot of abstractions to kind of piece together, and it's harder to understand collectively. And I think this reflects the advice in a philosophy of software design as well. So when we're deciding whether to combine or separate, the goal is to reduce the complexity of the system. And we might naively think that the way to do this is to make a whole lot of small components. And because each component is so small, each component is simple. But there's a cost to doing that. And the cost is that you end up with complexity just from the sheer number of components you have to kind of piece together in your head. And not only that, subdivision results in additional code to manage the components. So the complexity that's brought in through using a dependency injection framework, or through using things like an event bus to communicate between the disparate components. subdivision can result in duplication and boilerplate. And subdivision also creates separation. And this last point is really important. So methods that were together in a single class before subdivision may end up in different classes and even different files afterwards. And if there's dependencies between the components, then this separation is bad. Developers will end up having to flip back and forth between the components in order to understand the system. And if you were prone to writing really tiny classes, like I certainly was at an earlier point in my career, then you might have even had this comment on your pull request. You might have had, okay, I don't like the way you've divided this into tiny classes. I'm having to flip back and forth. And maybe you think maybe you thought the reviewer for your pull request was mistaken, that they didn't understand solid or they didn't understand clean code, because though that literature would have been pushing you to write smaller and smaller classes. So I think it's really great we have this canonical authoritative source in a philosophy of software design to point to say that excessive subdivision is bad. But what all this talk about single responsibility was actually a red herring? What if single responsibility didn't actually mean what we thought it did? It didn't mean just write all these small classes. And the way that single responsibility has been explained subsequently by the author of the principle is that it just means that a piece of code should have one ultimate owner. So if you have something like calculating employee hours, then that would be used by the CFO and the COO. So does it make sense to have a single class, because the business rules involved in each business unit might change? So single responsibility is just saying that in this case, when there's two ultimate business owners, you need two classes. So I don't know if single responsibility started out as being one thing and then it was changed and it was watered down. But regardless, you end up with this situation where single responsibility is either hopelessly vague and difficult to use, or it's extremely narrow and it's something we'd naturally tend to anyway. If we'd have classes to if we'd have business rules used by a CEO and CFO, I don't think we'd naturally combine those anyway. So if single responsibility is a bad way to think about this higher level decomposition, what would be some principles that we could use to guide us there? And a philosophy of software design gives us four principles there. The first one is bring together if information is shared. Now, I think this is really well explained or exemplified in Leland Richardson's talks about the philosophy behind Compose UI. So the way we used to do things in Android layer certainly was we'd have an XML layout, which was a view, and then we have a view model. And the view model would do calculations like calculating whether a particular view was visible or not. And then it would transfer that knowledge to the view by using data binding or by setting manually in a fragment. And what ended up happening in that case is the view model would start to actually resemble the view. You'd start to see all sorts of for example, you'd have in your view model a property that just modeled the visibility of one view or not. And all that information would effectively leak out of the view into the view model, and you'd end up with what Leland Richardson calls this hidden coupling, or you might understand as information leaking. So what a philosophy of software design is suggesting there is you can, when you get this hidden coupling or this leaking, it's actually a sign that two components are not actually separate and they should be brought together. And that's kind of what we're doing with Jetpack Compose. So instead of a view model calculating all this information about whether a certain element should be emitted or not, we really pare down the view model and have it concentrate on business logic. And then we just transfer a pared down object to the composable and let that perform the calculations about whether elements should be admitted or not. So we're bringing together some information. Now, of course, bring together to simplify the interface. And this is the overarching goal when we're making decisions about whether to separate or whether we're making decisions to bring together. We shouldn't be just following some really vague principle like single responsibility, and we shouldn't be aiming for something mechanical like that's just reflected in a naive metric like we need classes to be below a certain number of lines of code. It should be about making the most simple interface possible that's easy for our fellow developers to use. And of course, we should bring together to eliminate duplication. We almost don't have to explain this because we naturally tend to do this. The last piece of advice is to separate general purpose code and special purpose code. This is talking about layering, but let's go into more detail. So if a module contains a mechanism that can be used for several different purposes, then it should just provide that one general purpose mechanism. It shouldn't try and specialize that mechanism too early. So again, a really good example in Compose UI, Jetpack Compose. So the layering of Jetpack Compose, managing a material UI is seen as a special case of managing a UI. And managing a UI is seen as a special case of managing nodes in a tree. So it has this separation of general purpose code from special purpose code. We can see at the bottom layer of Compose, it's all about managing nodes in a tree. And you can see here we have a function for, or a class, sorry, for inserting and removing and moving nodes in a tree. And people have been able to build on top of this bottom layer. For example, Cash App has this library called Molecule that allows you to use this node management to create a state flow or another kind of a Kotlin flow. So let's imagine that Compose hadn't done this layering and they just mixed everything together and there was no way to separate out the node management from managing material UI. That would preclude solutions like Molecule, and it would also preclude using Compose to manage some kind of other UI, like some kind of UI that would come along in the future that we don't quite understand right now, but is a genuine possibility. So I think there's a really good opportunity here. Sometimes people come to me and they ask about topics for speaking in a conference or for writing articles about, and there's a whole lot of articles about applying solid and single responsibility, but not a lot of articles about how to practically apply the tenets of a philosophy of software design to your own code. And seems like fertile soil to me. I hope you enjoyed this talk. I'm going to put the slides up on Twitter and on Mastodon, and good luck with your problem decomposition in your own projects.